In this section, we are going to talk about the memory, which is one of the important logic block in the computer organization or in embedded systems. So what is memory? Memory is everything that we can store or retain in somewhere. A paper is also a memory. A hard disk is a memory. Flash drives are memory. So these are all type of memories that we can store the information and we can retrieve the information whenever we want. Now, when we consider the memories, we have to talk about their capacity, we have to talk about their organization, and most important metric in embedded system is access time, okay? Because it's an important performance metric and how long it takes to get the data from memory and so on. These are all important. Now, before we get into the details of the memories, there are a few things that terminologies that I want you to know about it. Now, what do we know? Bit is, we call it 1 or 0, okay? Nibble is just 4 bits. So, for example, 0, 0, 0, or maybe 1, 0, 0, 1. Then we also have byte, which is 8 bits. Let's say 1, 0, 1, 1, 0, 1, 1. Okay, this is an 8-bit. It's a byte. And we also have word, which is 16 bits. So, for example, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, 0. So 16 bits gives us the word. So when we talk about the memories, we talk about the powers of 2's. Okay, so for example, kilobyte. What is kilobyte? Kilobyte is to the power 10, which is known as 124 bytes. Okay, or it's just 1K, which we generally use, or a megabyte. Megabyte is to the power 20. Okay, and it goes like that. We talk about 1 million bytes. Okay, so 1 million. There's some extras over there. We generally call it 1 million bytes. And gigabyte to the power 30 over 1 million, and terabyte to the power 40, 1 trillion, and so on. Okay? Now, when we consider these memories, what is more important is in order to derive these memories with their sizes and the capacities, so for example, we say 16 megabytes of memory. So what is 16 megabytes of memory? 16 times megabyte is to the power 20. Okay, or we can say 16 is to the power 4 times to the power 20, which is to the power 24. So 16 megabyte is equals to the power 24. We are always trying to represent them in powers of 2. Okay, let's get into the memories. Let's see different types of memories and let's talk about them a little bit. So we have got 2 types of memory commonly used in the microcomputers. They are RAMs and ROM. RAM and ROM are the two types, and they have a different characteristics. RAM is random access memory, ROM is read-only memory. And RAM is also known as read-write memory, and ROM is just we are reading it from it. So RAM, when you turn off your device, you lose all the data inside. But ROM is not like that. Even if your computer is off, your data is still there. Okay, so we are using RAM type of memories for temporary storage, which the programs are running and the CPUs keep getting data from it and so on. We call them volatile memories. And ROM contains the programs or maybe some important information related to the devices or the computer. And the data is permanent over there and cannot be changed by the user. And you don't lose it when the power is off. So we call them non-volatile memories. So there are different types of memories like mask ROM, PROM, EEPROM, EEPROM, flash ROM, which we are going to talk about them, and static RAM, dynamic RAM, and non-volatile RAM in a minute. Now, before we get into these different types of memories, as I already mentioned about the internal organization of the computers, where we talked about the buses like data buses, control buses, address buses, and the resources around these, um, as they carry out information or a data or an address to the CPU or from the CPU, what engineers are generally talk about is the processing power of a computer is totally related to the size of its buses because buses are carrying the data. So that's actually affecting the power directly. So, for example, 8-bit bus can send out a byte at a time, right? So 8-bit, you send out an 8-bit, which is 1 byte. Then once it's transferred, you can send another one. But a 16-bit bus, which is a wider bus, can send out 2 bytes at a time, which is twice as fast. Okay, so processing power of a computer is totally related with the buses that you have gotten in the internal organization. Right, so let's get into the memory organization and let's see what type of devices or the memories that we can have. Now, the number of bits that each location within the memory chip can hold is always equal to the number of data pins on the chip. This is important. And how many locations exist inside a memory chip? That totally depends on the number of address pins. So that means the number of locations within a memory circuitry is always equals to the power of the to the power of something number of address pins. Therefore, the total number of bits that the memory chip can store is equal to the number of location times the number of data bits per location. So, for example, memory chip contains 2 to the power x locations. Where x is the number of address pins. Now, let's say each location contains y bits. Okay, and Y is equals the number of data pins on the chip. So that means we have got 2 to the power x locations. X means the number of address pins, and each location contains y bits. Y is the number of data pins. And in the end, the entire chip will contain 2 to the power x times y bits, where x is the number of address pins and y is the number of data pins. So one of the most important characteristic of the memory chip is the speed at which the data can be accessed. This is a design metric or important metric as a performance. So in order to access the data, the address is presented to the address pins, the read pin is activated, and after a certain amount of time has elapsed, the data shows up at the data pins. So shorter this elapsed time, the better and consequently more expensive memory chip is. So the speed of the memory chip is commonly referred to as access time. And access time of memory chip varies from a few nanoseconds to hundreds of nanoseconds, depending on the circuit technology used in the design and also in the fabrication process. Okay, so let's get into these different types of memories and let's see how they are different from each other. Okay, so ROM types, mask ROM and programmable ROM. Now, mask ROM, it's actually manufactured and programmed while manufacturing it. Okay, so we are actually burning fuses or transistors in there. So it's like a hard wired data over there. Okay, it's really cost effective. You can manufacture large quantities. You know what is in there. Its content is fixed, like a device IDs, manufacturer IDs, the dates of the manufacturing, and so on. On the other side, we have got ROM, which is a PROM, which is programmable ROM. And programmable ROM, you can program it one time, okay? And it's a non-volatile. You can just program it once and you can use it. You cannot change the data inside of it. So you have to apply some voltage over there. Again, by applying a voltage, we are actually burning the transistors or fuses inside of it, which you cannot change it or alter it anymore. Also, we have got erasable programmable ROMs, and EEPROM is one of those where there's a, as you can see, there's a small window over here where you apply a ultraviolet radiation so that you can erase it. This is an old-fashioned technology as well. It can take 20 minutes to erase it, the entire contents, and then you can reprogram it. So in order to program this type of chips, you have to erase the contents first. So what we do is we remove it from the socket, we place on a special equipment where we apply the UV light for 20 minutes, and then what we do is to program it, we place it on a, there's a special ROM burners, programmers that we call it, and we burn the code into it. Again, we are applying some kind of voltage in order to burn it. Now, another type is electrically erasable programmable ROMs. Now, they are erased electrically and instantly with a regular computer. And You can easily program it between 1 to 10 milliseconds or erase separately in 5 to 50 milliseconds. They're costly than EEPROMs, but due to transistors inside, but they're more flexible actually. So we can easily reprogram them. And the good thing about EEPROMs are you can select which byte to erase. So you can select a specific byte and erase it. Another type of EEPROM is a flash EEPROM, which we generally use nowadays. They are called flash EEPROM because they are erased in a flash. So you are actually erasing large chunks at once. So each chunks can be programmed very quickly, like 10 to 100 microseconds. So if there's an F in front of it, that means it's a flash memory. So as I already said, the important about the flash memory, the erasure of the entire content takes less than a second, or a flash. That's why it's called a flash. It's electrically erased, and that's why it's called a flash EEPROMs. Now, major difference between EEPROM and flash EEPROM, or flash memory. So when the flash memory contents are erased, actually you are erasing the entire device. But as I already mentioned, when you are erasing the EEPROM, you can just erase a desired byte. Okay, you don't need to erase everything. And in flash memories, contents are divided into blocks so that erase operation is done block by block, unlike EEPROMs. But flash memories, they don't have byte erasure options in the end. So these are ROM types memories, and RAM type memories, which we have got SRAM or static RAM. Now SRAMs or static RAMs, they are like a latches. So if you do remember latches from logic design, latches or flip-flops that we call them, they don't need refreshing in order to keep data in there. They are really fast. Disadvantages as you need to have lots of flip-flops or latches in there. It has high power consumption. It's expensive because number of transistors that you use over there. Okay, so for example, 6116 SRAM, 2K by 8-bit, 2 kilobytes, or 16,000 bits of capacity, which access time is as fast as 15 nanoseconds. Okay, and now the problem with the use of the flip-flop for storage cell is that each cell requires at least 6 transistors for implementing a latch, and the cell holds only 1 bit of data with 6 transistors. Okay, and then they developed a 4 transistor version, but still too many. Now, when we consider typical SRAMs, as you can see from the diagram as well, we have got address pins, as you can see, A0 to A7. We have got write enable, so we have to enable write enable pin so that we can enable writing on it, or read enable, or like OE, or output enable for reading data. We also have a chip select. These are all active low signals. And the chip select is used to select the memory chip because you might have different memories in there and you can select one of those. And IOs, as you can see, we have got in and out where 8-bit data lines given an organization over there. So address and inputs, outputs. Now, dynamic RAMs, which we generally use in our computers, because SRAMs are fast, they are generally used quite close to the CPUs, but DRAMs, dynamic RAMs, we use it outside of the microcontrollers as well, which are closely again to microcontrollers or microprocessors. And they are first introduced in 1970s by the Intel Corporation. Their capacity was like 1024 bits. And it generally uses a capacitor to store each bit. So you're actually charging a capacitor over there, and you don't need any transistors to build these cells. However, the problem is as the capacitors are slowly discharging in a time, you have to refresh it. So you have to recharge it so that you can hold the charge over there. And they're slower compared to the SRAM memories. Another memory type is a non-volatile RAM. So non-volatile RAM is made up of SRAM, as again with the latches, but it has a built-in battery over there. So whenever the power is off, battery is running over there. It's like a EEPROM memory array and the control circuitry. They're quite fast, infinite program erase and cycle, program and erase cycles, and they are also non-volatile. The only problem is they're also expensive. Okay, so it combines RAM and ROM functionalities. Now, one of the important things that we need to consider about the memories are the organization. Now, when we talk about ROMs, the ROM chips have 8 pins for data, for example, and this is not the case for DRAM memories, which can have 1, 4, 8, or 16 organizations. So with the different types of products, you can have different data pins for it. Now, another important thing is memory access. So how are we accessing the memory from the CPU? Now, you can see a long data over here, which is a 16-bit or one-word data, which has got a low byte, low 8 bits, and high byte, high 8 bits. So this is actually the address of a memory. If we want to decode, it's 0101. We are just reading like a typical 4-bit number. So 0101 is 5. And then we have got 1100, which is C. And then we have got 0001, which is 1. And we have got 0110, which is 6. So addresses are generally represented with hex, and they are represented with a dollar in front of it. That represents 5C16 in a memory address, where 34 is stored over there. And the 34 is represented as 0011, 0100. This is 3, this is 4. Okay, and that's how the data is stored. So this is the address, and this is the data. Now, when we consider these memory accesses, another important thing is how are we going to connect this memory to the central processing unit? Because it's important to send data and retrieve data from memory to do some operations. Now, CPU execute instructions, it has to fetch, do some operations, and send it back. Now, this is a typical memory block where we have got write enable, read enable, or output enable, and chip selects, data lines, and address lines all together. Now, we can see how we can access it, as I already mentioned, if you want to write or read from a memory. Now, we provide the address if we are writing, okay? Then we select the chip. So we are having an active low over here. We select the chip that we want to write to, okay? And we provide the data to it. Now, then what we do is we activate the write enable so that we can write on that specific memory. We have a short amount of data setup time, okay, that we need to keep it, the write enable. Then we can provide the data. And then we also have data hold like the memories, like flip-flops, so that we can have the valid data between that time. Then this will be written into the memory. If we are reading memory, be careful over here. Write enable is always high because we should not go down. We are not writing. We provide the address that we want to read and we select the chip that we want to read, memory chip. And we also enable output, enable signal so that we can get the data. So from here at the start that we start to provide the address until we reach the first sign of the data, this is the address access time, okay? So we have the valid data on the data line after a certain amount of time. We will see these in details when we get into more hardware-specific implementations. Now, like we connect memories, we can also connect I/O devices to the central processing unit. So CPU should have lots of pins around it, like connecting mouse, keyboard, sound card, graphic card, network cards, different types of I/Os, memories. Everything has to be connected to the CPU so that CPU control all of those. Now, there are different types of structures that we can do in order to have a connection between the CPU and other devices. One of the methods is we can use a shared bus, address bus or data bus or a control bus, like you can see in the figure. Okay, so these are all the I/O devices. They are sharing the common bus, but they have a different addresses that we can reach it. Now, when we consider I/Os and memories together, you're actually increasing the number of buses or maybe wires. So you can have a higher cost because you are increasing the size of your system in the end. So we need to be careful while we are designing this type of circuitries or the systems. What you can do is you can also use a shared bus between I/Os and the memories. Okay, and this is showing the example over here. Now, if you have one memory over here, then your chip select does not need to be connected to anywhere else. That means it's always activated. Whenever you want to read, you provide the address. Okay, so each of those has got their own addresses. Now, we have to be careful here. Why? Because I/O address is also 0, and also memory address has got 0, a 0. Okay, so how does CPU is going to understand which address to write to? Okay, so we can say, how could we manage it? To write to memory or to write to an I/O? Okay, so we have to be really careful over here. We have to have some options over here. Now, one of the options is we can have an extra control signal, which we call it I/O for the memory, and that chip select is directly connected over there. So whenever that signal is activated, that means we can write it to memory. If that signal is not activated, we can write it to the IOs. And we can also reorganize the address pins, okay? We can also do that in order to write to it. Now, one another approach is to use a logic circuitry for the chip select. If you have multiple memory devices and multiple IOs, then we need some kind of chip select to select the partition or select the address that you want to write. So, for example, you have to enable the chip select when the address is between 0 and 15. So how do we do that? The question is, how do we do that? Now, the CPU provides the address of the data desired, but it is the job of the decoding circuitry. So we need some kind of a decoding circuitry to locate the selected memory block. Now, in order to understand the concept of the decoding circuitry, we have to look at various methods using the decoding the addresses. Now, memory chips has got the chip select, which must be activated in order to access the contents of that memory or to write to that memory. Or this chip select sometimes is called also chip enable. Now, the data bus of the CPU is connected directly to the data pins of the memory, as you can see, the blue line. And the control signals, right, like read or write, are connected to the CPU from the control signals, as you can see. Now, in the case of the address buses, while the lower bits of the address from the CPU go directly to the memory chip address pins, the upper ones are used to activate the chip selects of the pin memory. Now, it is the chip select pin that, along with the read and write, allows the flow of the data in or out of the chip. So no data can be written into or read from the memory chip unless the chip select is activated. So how are we going to activate that chip select? That is the question. Now, simplest method of constructing a decoding circuitry is the use of a NAND gate. If you do remember the NAND gate from logic design course, we were using NAND gates with an active low output for decoders. Now, the output of a NAND gate is an active low, and the chip select pin is also active low, which makes them a perfect match in this case. So if you have a chip select as an active high, you can use AND gates. Now, how do we use that? So the solution is write the address range in binary, separate the fixed part of the address, which is not going to change. As you can see, these are all fixed. And using a NAND, design a logic circuit whose output activates when the fixed address is given. So address 3 to 0, these are changing from 00 to 111. But address 7 to 4, they're all fixed. It's always 0. So in order to activate it, all zeros. Now, for NAND gate, all zeros are going to fed in, okay? And they are going to be inverted to become 1. And when they fit in to the NAND gate, they become 0, which is going to be fed into active low chip select. This is what we need to do. Now here is the question. Design an address decoder for address of 300H to 3FFH. Now 300H, 3FFH. So 0011, 0011, and the rest is 0000, 0000, 1111, 1111. So this is the fixed part. Those zeros has to be inverted, and those one has to be coming as they are. So now I can have a NAND gate decoding which will activate the chip select. That's all we need to do. That will be the answer for it. Okay, so this is how memories are working and how they are operated and how their capacities and organization is formed with the different types of memories.